All right, so we have been talking about volumes, and we will continue doing this. Last time we talked about this method. Then the last example that I did was Washers method, which is basically the same thing as this. It's just that you take into account that there is a little hole in the solid because the region that you rotate is somewhat separated from the axis of rotation. Okay, it's not completely adjacent to it. And we did one example, but that was all we did. So now I want to do more examples, like write down the formulas and so on, do examples, and then we will talk about cylindrical shells, okay, which is another method. All right, so again, the point here is that the washer method is exactly the same idea as this method. So here, so this is used when the region that is rotated is not completely adjacent to the axis of rotation, okay? So there will be a little hole in the solid that we obtain. And remember, the general idea is we will always use rectangles as a reference. So in this case, the rectangle, once again, is going to be perpendicular to the axis of rotation. So when you decide to put the rectangle perpendicular to the axis of rotation, you will either get this method or washer. Which one is it? Well, this if there is no hole. Washer if you see that there is a hole. So let me show the picture. Let's say that we have here our axis of rotation. We are rotating with respect to this line, and then our rectangle will be placed like this. Okay. The other situation would be that our axis of rotation is a horizontal axis, something like this. So then our rectangle will be placed like this. I should have switched the pictures, but that's okay. It's going to leave it like that. All right, so these are the two cases that you can get, okay? So when your axis of rotation is parallel to the y-axis, so it's a vertical line, then the rectangle has to be formed, okay? Perpendicular to the axis, like pointing towards. If you extend, what I mean when I say perpendicular, what I mean is if you extend the rectangle, it will be perpendicular to the axis, because here it's not really touching, okay? And same thing here. This is the case when the axis of rotation is horizontal, parallel to the x-axis. Okay, there are some quantities that we need from here. So, for example, as you know, when we rotate, we're going to be creating a disc with a hole inside. So, this one will generate this sort of picture. And then this is the something like this. Okay, just gonna do this. The point is that there is a thickness to this. Okay, here we go again. So let me just do it the usual way. So we have a rectangle. When you rotate this, you're gonna produce a copy over here. Okay, and then something like this. And then it goes this way. This is in the background. This here in the back. So again, you have to think of this rectangle as sweeping around the axis. Okay, so we have our axis right here in the middle. Okay, and then we're creating a sort of disc. It has a certain width attached to it. But then remember there is a hole inside because we have this separation. That separation is going to create a hole, which is another disc. Okay, we call this a washer. And what's important here is this distance, which I'm going to call it little r in. And then I also care about this distance, which I'm going to call it big R. So R out. Let me do everything in red because blue is the other side. So the picture here is very important. R in represents the distance between the the rectangle and the axis of rotation, and R out is from the farthest point of the rectangle, the distance from the farthest point of the rectangle all the way up to the axis of rotation. You see that from the picture? That's important. Why do we call it like this? Because R in happens to be the radius of the little disc, right? The hole that we have. That's what R in represents. That's the radius of the hole, and then R out is the radius of the big disc. So in this picture, R out is represented by this. You okay with this? And now, of course, the width here. Let's see, what variable should I use? Should I use delta y or delta x for this? Delta y, because this is perpendicular to something that's vertical. So that means your region, you're gonna be filling the region with rectangles this way, from bottom to top. Understand this? Remember, every time, whatever axis your rectangle is perpendicular to, that's your variable of integration. So here, in this situation, you are integrating with respect of y. So I'm gonna call this one delta y. And delta y is, you know, the thickness of this guy. And then on the other case, we have something similar. So after rotation, what's gonna happen is, let's see, we have a rectangle here. Then it gets mirror image over here. And then something like this. Okay, leave it like that. So we kind of get this the same dish, but in the other position. And then once again, the same thing. R in is the distance between the closest point of the rectangle and the to the axis of rotation and the axis of rotation. So the separation, the hole. And then R out is from the farthest point, the distance between the farthest point of the rectangle to the axis of rotation. Okay, so that's R out. I said I was gonna do all of this in red and I did it in blue again. Not sure why I did this in blue. Okay, so in this picture, again, R in represents the radius of the hole, which is that little disc, and then R out, again, think of our axis of rotation is here, and this is R out, the radius of the vehicle. Okay, so from this picture, it's pretty easy to see what the volume of these objects are. What, by the way, before I do that, what's the variable here in this case? That would be delta x because it's perpendicular to something horizontal, the x-axis, okay, parallel to the x-axis. So that's the thickness of your washer. So in this case, the volume is going to be calculated as the integral. Let's say, so I'm going to say from C to D because this will be with respect of y. And then we're going to integrate the area. So the solid that we're going to obtain, we actually integrate it by using the formula for the volume or something like this, because this is what approximates a solid from the inside. Remember, the idea is pretty simple. Volume of the outside minus volume of the inside. So basically, that's going to be area of the base, which is pi r squared, but then you have r out and r in. So r out squared of y minus r in squared of y, and then the delta y becomes dy. So if you distribute all these things, the pi r out squared times dy, that represents the volume of the outside, okay? Remember, it's area of the base times the thickness. The thickness is represented by dy here in the limit, it becomes pretty small, etc. So pi r out squared is the big volume, and pi r in squared is a small volume, and we're subtracting those two. Okay, so it should be pretty straightforward to remember this formula. So this is basically the same thing as this method. It's just that you have to subtract the whole. So that's why you have this r into the game. All right, and then in the other scenario, we have the volume, the same thing, but now everything is with respect of x, right? So the integral from a to b of pi r out squared of x minus r in squared of x dx. The delta x becomes dx in the limit. We okay with this? So these are the formulas for the method of Washers, okay? And when do you use it? your rectangle has to be perpendicular to the axis of rotation, and there have to be some sort of separation between your rectangle and the axis at some point, okay? If it's always touching the axis, then you're using this because there is no hole. So there's no R in the picture, that's all. All right, questions about these formulas? Let's do examples.
Sir, so here we're finding the volume of the small rectangle, right?
Yep, okay, so the formula that I just put here is what you get when you have a solid. Okay, so I guess, let me say, this is when a region is rotated about, so in this case, we're rotating about a vertical axis. About a vertical axis. That's the formula. And then this one is when the region is rotated about a horizontal axis. So region rotated.
So the region here would be like the rectangle, right?
No. I mean, if you rotate a rectangle, that's the shape that you get. If this is the shape that you get, the volume is the same thing that we have here, but without the integral. You just do pi r out square minus pi r in square times the delta y, and you're done. Yeah. But that's not interesting. What's interesting is what if you have another region? And again, what's going on behind the scenes, just I don't want to repeat, like to rewrite the whole thing that we did before. Just the idea is that now you have a region, you fill it with rectangles. When you rotate, you create your solid, but then those rectangles that are approximating the region will create washes like this inside your solid, approximating the volume. So if we add those, that will be an approximation of our actual volume, and in the limit, taking infinitely many, that's why you have an integral. So if you integrate the expression of the volume of the washer, you're gonna get the volume of your solid. That's what's happening here.
This is probably way beyond this, but in this semester, would we learn like a spring where it's kind of like a washer, but then also vertically out?
You do that in physics. Yeah, if we have time and you're interested in those things, maybe at the end of the semester we can do some physical applications. I want to do differential equations, but we'll see what is. We'll see when we get there. Yeah, but in physics you will see that. Okay, so again, this formula is for the actual volume of the solid that you obtain when you rotate a region that's not a rectangle. You rotate a rectangle, you don't need an integral to calculate. Yeah, exactly. That's the point. You don't need the integral. Okay. All right. So let's do examples. Again, what I recommend to you is do not memorize the formulas. Just make sure that you understand what we're doing, because this is kind of pretty easy to remember. Okay. Just by seeing the situation, it should not be too difficult. All right. We already did one last time, so let's do another one. So find volume. And let's call this number 1, and let's see, the region is given by the following functions: x equals e to the 2y, x equals y squared, y equals 0, and y equals ln of 2, and we're going to rotate about the y-axis. Okay, and then let's rotate about the y-axis. All right, so again, in all of these problems, the first thing that we need to do is we have to go ahead and sketch the region to be able to take a look and see what is it that we have, and then we decide what to do. All right, so the first observation here is, and notice that I gave you everything the other way around. Instead of telling you y equals something, I told you x equals something, okay? So when it comes to sketching, it could be a little bit uncomfortable to draw it this way, because this means that you should think of y as your x, as your input, and x is your output. Instead of doing that, let's rewrite the equations in an equivalent way, and then let's draw it the way that we're used to, okay? Just for drawing purposes. It doesn't mean that I will use the equations that I'm about to write. I'm just gonna do them for drawing purposes, okay? So note, x equals e to the 2y. So as a curve, so remember, what is the graph of this is the collection of points x, y, so that when I put them here, they, they solve the equation. So whatever equation that I write here that's equivalent to this one, I can use it also to graph. That's what I'm about to do. So this is the same thing as saying that 2y equals ln of x, right? And then that's the same thing as saying that y equals 1/2 times the natural log. In other words, this is something that we can easily sketch. We know the graph of the ln, and 1/2 means a vertical compression by a factor of 2, right? You're compressing the graph. So we know how to sketch the first curve. Now I'm going to do the same thing for the other one. Actually, the other one from pre-calculus, you know that this is a parabola, right? But it's going to be a parabola that opens either right or left. Instead of up or down, it's right or left. Which one is it? Right. So you understand this? You know it's either right or left because it's the other way around that you're not used to. Now, where does it go? Well, just think about it. What is this telling me? This is telling me that x must always be positive because x equals y squared, right? So you better be pointing to the right because your x's has to be positive. If you put a negative here or if you put a negative here, then that means that it has to open to the left because x is always negative, okay? So that's a quick way of seeing that. All right, so I don't need anything special for that one. And then the other two lines are horizontal lines. So let's draw. So we're going to sketch the natural log function. That will be my red curve. So the natural log function, remember it looks like this. With the added thing that we need to compress it by a factor of 1/2. So how do we see that? For example, this is still 1. But when you plug in E, let's say E is somewhere over here. When you plug in E, normally you will get 1, right? Here we're gonna get 1/2. So the scale is super weird, but I'm gonna do it otherwise. They're gonna have a tiny region, okay? So I'm going to exaggerate the scale on the y-axis. Otherwise, I'm gonna have a super small region to show. Okay, so this is the red function, and I'm not putting any labels because I don't know which one I'm gonna use yet. I don't know if I'm gonna use the y equals version or the x equals version, okay? First, I want to draw and see what is it that we have. Remember, after you place a rectangle, that tells you what version to use, okay? All right, so let's graph the next one. The next one is x equals y squared. Okay, so we know that's gonna be a parabola, and it's gonna look like this, right? So there will be some points of intersection. It's gonna cross over here, and then it's gonna cross. It may or may not cross over here. I think it's not gonna cross because this is a very slow function. This function is super slow. So most likely they are not gonna cross. But let's figure it out. How do we figure it out? We need to solve the equation, right? So and we need to have y equals 0. Okay. So let's solve the equation anyways. So we need to figure out when is it that the two functions equal to each other. I'm gonna solve it from here, okay? Or I'm gonna look at it from here. So that means e to the 2y equals y squared. When does this happen? Okay, now here we have a problem. That if you use the techniques you know from pre-calculus, you're not going to be able to solve this equation. Why is that? From pre-calculus, what is that you will do? Then you will use ln to bring this y down, right? But if you do that, then this y is going to be inside the ln. Then you will use e to get rid of that y, but then the other y gets trapped. Okay? So situations like this, you cannot solve it by straightforward algebra means. So what we need to use is numerical methods. You know how to do this by using the mean value, the intermediate value theorem. Yes? Do you know what I'm talking about? Yeah. For example, when a function is continuous over an interval, if it changes sign, then it has to have a 0 in between. You can take advantage of that to figure out what would be a solution for this. Now, luckily for us, we don't really need to solve this completely. And I'll show you why. Because look at the region. It's not just the region between those two functions. If it was between those two functions, unfortunately, I know there will be a solution somewhere in here. Okay, actually, yeah, I know there will be an intersection somewhere in here. But this one, I'm pretty sure there will be none. Because the thing is that this grows way slower than this one. For example, ln, let's see, just to give you an idea. Remember, this top curve here, the blue, is a square root function. Okay? So let's see, when you plug in 1 for ln, you're here at 0. Here you're already here at 1. If you plug in 2 for ln, what's ln of 2? ln of 2 is 0 point something because ln of e is 1. So 0 point something divided by 2 is even more 0 point something. Here you are at 1 point something. And the farther away you go, this is going to be growing, but very slow, and this one is a little bit faster. That's one way of seeing that they are not going to cross. Now, really what you should do is go ahead and compute the difference of these two functions. It 2y minus y squared, and just figure out when is it that this happened. We know there will be a solution to this equation, and we're expecting this to be between 0 and then 0 and 1, because yeah, it should be between 0 and 1, because this part here, then it becomes positive. So for example, if I plug in 0, what do we get? I'm going to have 1 for this function, because it will be 1 minus 0. If I plug in 1, what do we have? E squared minus 1. So 0 is not good. E squared minus 1, that's positive. Oh, because this is with respect to the y-axis. I need to know who is this guy. It will have to be with respect to the others. Hold on, it's just that I'm not solving for x, I'm solving for y. Okay, so instead, I would say, anyways, we don't need this for this problem, but in case that you need it, you have to do this analysis. So it would be this equals square root of x, and the other option is this curve equals negative square root of x. What is this negative square root of x coming from? If you solve for y in the second equation, you will get y is plus or minus square root of x, right? So the positive one is the top guy. This top equation should not have a solution, okay? I don't think it's going to have a solution. The bottom equation, the one with the negative, is the one that I'm expecting to have a solution, as you can see from the picture, okay? But the reason why I'm saying that we don't really care about that is because, anyways, our region is, yes, okay, this function, but then we have the y-axis, we have the line y equals 0, which is the x-axis. So that means I'm not even looking at this because we're cutting this at the x-axis, and then y equals ln of 2, which is, we have to see whether it's bigger or not than 1/2, but we can calculate that pretty quickly. So it will be a horizontal line up here, so it would really just be this little piece right here, okay? That's all. So really what we need to be able to figure out is which one is on top, the blue or the red. I already told you the red is going to be under, but you need to convince yourself, okay? And we can do that by taking, so basically we need to show an inequality, okay? So we need to show, we need to argue that square root of x, now I'm talking about the top part, the square root is bigger than 1/2 ln of x. You can do that by showing that the difference is an increasing function. Why am I doing this? Because then you can use calculus 1. Remember, positive derivative means your function is increasing, okay? So that may help. But let me see if I say something more here. Because if we didn't have, for example, the y equals 0, if we didn't have this would be very complicated. Because if we didn't have that, then we needed to know this point down here, because this piece right here would be part of our region. Okay? Yes?
So are we going to get a problem like on the test or as a homework where y won't be equal to 0? We'll have to solve.
I'm telling no, because here is with this one in particular. If you get it, it will be something that you can solve pretty easily. This equation you cannot solve it easy. You cannot solve it algebraically. You have to use numerical method. Like this is not a nice number. This is not 3/2, or this is not 1/2 or 3/4. This is a weird number. This right here. But it exists. And I'm telling you, one way to find it is by approximating this. So let me just show you how you will find that number. So I will write square root of x plus 1/2 ln of x equals 0. Okay. Just bringing this side over here, and then the question is, when is this function equal to 0? Okay, and then the claim is that between 0 and 1 there is a solution here. So let's see if we find it, and we know actually from the picture that's the only solution that we have, because the natural log function, it keeps going this way, getting closer and closer to the y-axis, and this bottom part, negative square root of x, it just is going farther away from the y-axis. The only case that they meet is here. So that's the only place where we're expecting a solution, okay? And just to figure this out easily, let's see. We cannot plug in 0 because this function is not defined as 0. So I don't know. So definitely, if you pick 1, you're gonna have 1 minus ln of 1 is 0. So you're gonna have something positive. So let's pick, let's say, something super close to 0. So let's say 0.1. So what's ln of 0.1?
Where did you get this square root of x?
That's this function right here. This is x equals y squared, right?
Oh, okay.
So the top part is y equals square root of x. The bottom part is y equals negative square root of x. So I'm starting the bottom part. I want to see when is it that these two functions, the red and the blue, meet, okay? So you need to, if you want to do this in general, you need to analyze the two questions, okay? So this one down here and the one on top. I'm analyzing the one down here. From the picture, we can see there is only one solution, okay? They only cross once. Let's figure out how we can find this point. You will just do it numerically. They put it on the computer and we will do it for you. But so you can see that indeed that's the case. This is what you do. You want to solve this equation, 1/2 ln of x equals negative square root of x. So to solve this is equivalent to solve the bottom one. It's finding the zeros of this function. So will this function ever be 0? Let's see, we know this function is continuous on its domain, right? The domain is from 0 to infinity, not including 0. So I'm gonna call this function f. Let's call it f of x. So f of 1 is gonna be equal to 1, okay? So I cannot plug in 0 into the function because ln of 0 is not defined. I'm gonna plug in 0.1. I want to get something very close to 0. So let's plug in 0.1 and see what we get. So we're gonna have square root of 0.1 plus 1/2 ln of 0.1. And we have to see, is this a positive or a negative number? I'm expecting it to be negative. So 0.1 ln, okay, divided by 2, that's negative 1.15, etc., and plus square root of 0.1. So we get about negative 0.83. The point is that is less than 0, okay? So here is 0, which is a forbidden number. Now, because ln is not defined as 0, here is 0.1, here is 1, and then we know that the value of the function at 0.1 is negative, and the value of the function at 1 is positive. Now, this one is a continuous function, okay? The function f is continuous. If at 0.1 is negative and at 1 is positive, remember, continuous means you can draw it without lifting your pencil. What do you think is going to happen? The function is somewhere down here, like a negative 0.83, and then when you plug in 1, you get 1. So you have to join these two dots. From here to here. What do you think is going to happen? It has to cross the x-axis at some point. So when whatever the graph is of this function, somewhere it will cross. We need to figure out what this is. Okay? Now, how do you do this? One way is taking advantage of this idea. So this tells me that my answer is going to be between 0.1 and 1. It's too far away. So what do? We split this into, let's say, 10 little pieces. And then you evaluate the function on all of those 10 little pieces and see where the change of sign happened. And then you already know that your answer is between those two. Then take that little interval, split it again into 10 pieces, and repeat the same process. But you don't do that manually. You do it, I don't know, in Excel or something like that. That's what a computer does for you behind the scenes. When you put in Wolfram Alpha or any graphing calculator solve this equation, that's what they're doing. They're doing numerically. They don't do it symbolically in this case. Okay? Again, I'm saying this because, you know, if in general out there, most of you are going to be engineers and you may encounter situations like this. Rarely you're going to encounter functions that the solution will be 2, 3, 4. Okay? That's not going to happen. That's not going to happen. It may happen, but most likely not. So in that case, you need to be able to use your knowledge to see if you're going to have a solution or not. Again, from the picture, we see that we have a solution, and moreover, the picture tells you that that solution will be less than 1. Okay, so you already know that will be somewhere in here. Why 0.1? Because I cannot pick 0. I was going to pick 0, but I cannot because it's ln of x. So I just wanted to pick something close to 0. Maybe if you pick 0.5 and it works, then we're already closer to what the solution should be. Okay, and then this is called the It's an enhancement of a bisection method. So in general, what you do is split in half, evaluate at the middle, and then see whether it's in this half or this one. It's in this one, okay, split in half again and continue, but that's too slow. That's why I was saying do it in 10. We're gonna use computers anyways, okay? For example, anybody here in computer science? Do you have to do programming? Most of you have to do programming, right? So how do you search for let's say that I give you a list of 1 million numbers, and you need to search for a number, for a given number. You have 1 million person, the age of 1 million person, and this is ordered. This list is ordered, and you want to search for a person. Okay.
Geez, Boolean logic.
Let's say that the ages are different also. Well, that's impossible. Yeah, because then
Just talking about like doing a basic.
let's say that you have 1 million numbers, whatever it is, not age, let me not say age, and you want to look for a number inside that list. And the list is ordered. You already know the list is ordered. Okay? How do you do that in an efficient way?
Boolean logic. If it's less than this, then do that. If it's more than this, do that. If it equals
But what is this? But what is this?
What do you mean?
If it's less than this, more than this, what is
Boolean
this?
logic, right? Is that what you're
What do you
talking
mean by Boolean logic?
Would it be the middle point?
Exactly. So that's what you use, the bisection method, right? So this is a general idea that is used everywhere. It's not just here. This is what you use when you want to look for something. You have something that's ordered. How can you look for inside this big list? Okay, split it in half, and then say, okay, where is my object? Is it big? It has to be something that you can compare. Okay, is it bigger than the half or smaller than the half? If it's bigger, you already know it's in this piece, and you can ignore half of it. Instead of going through the entire list and saying, is this one no? Is this one no? Is this one no? That's too expensive, right? What if the object is actually the last one? And you're gonna go through 1 million items to find it. So you compare with the half, and then you say it's bigger than this one. Okay, it's over here. It's less than this one, then it's in this half. So ignore the other half. Then you repeat the process. So you are doing this in a loop, half again, and compare, and you keep on doing it. Or if it's equal, then you found it, and then you're good to go. Do you understand the idea? That's what I'm using here to be able to find this. Just half and then compare. Evaluate it. If you get 0, you're good, done. If not, okay, is it positive or negative? If I get a positive number, that means that because it was negative and then my answer was positive, then it's gonna be between 0.1 and that half. Okay? If the half, when you evaluate in half is negative, then okay, it's between that and 1. Then half again and repeat. An enhancement of that is instead of doing half, do it in 10. And that way you move faster towards your answer. You reduce 1 decimal place at a time. Okay? Anyways, that's not even relevant because we don't need it. But this is if the y equals 0 was not there. That's how important. That's why sometimes we really need to carefully think about the problems that we give you. Because if I don't write this y equals 0, you have to go through all of this, because that would imply that this little region here is included. Okay? So, but it's not. Anyways, so did you understand this more or less? So I'm gonna rewrite the picture. I'm not gonna erase it because I want to leave it there for your reference if you want to look at it later, but I'm gonna rewrite it a little bit nicer, okay? So note the above is not relevant to our problem. Thanks to the y equals 0 boundary. If we didn't have that there, you have to go through all of these things, okay? If that was the question, or something similar to that you couldn't solve, I arrive here, oh, okay, let's find the point of intersection. The moment that I saw this, I was like, that's it, we're stuck. Okay, not stuck, but then you have to then approximate stuff. All right, so in any case, let's go back to the problem. Again, the region. So we have our ln function. This is 1 over here. Then I know that I'm gonna have, I only care about the upper half because they say the x-axis, so I only care about the upper half of x equals y squared. So it's gonna be something like this. And then we have y equals 0 and ln of 2. Let's say ln of 2 is over here. Then we have this horizontal line. So this line here is y equals ln of 2. And let's see, what is this point? So remember that the red point is y equals, the red curve is y equal 1/2 ln of x. So we're gonna get ln of 2 if I put a 4 here, right? If I put x equals 4, that's 2 squared. The 2 comes down and cancels with the 1/2. So this happens at 4. So that happens when x is 4, and then for the square root function, we get square root of x equals ln of 2. So x is gonna be ln of 2 squared. So that's about 0.48. So you see, like, square root function is super slow. I mean, the ln function is super slow.
Professor,
Yes.
where'd you get the 4 from? Do you plug ln of 2 into 1?
I want to know what x value will give me ln of 2, right? In other words, you put here ln of 2, y equals ln of 2, and so for x. You can do it easily because if you put a 4 here, that's 2 squared, the 2 comes out and cancels the 1/2, and you get ln of 2, right? So ln of 4, what is this? That's ln of 2 squared, which is 2 ln of 2. Remember the property of ln, you can bring exponents down, right? But you have a 1/2 in front, so it's gonna cancel and you get ln of 2. If you want to see the long story, you will need to solve this little equation. ln of 2 equals 1/2 ln of x, right? And then, you solve it. So at the same thing as 2 ln of 2 equals ln of x, that's ln of 4. And as you know, the natural log function is 1-to-1. So that means if ln of 4 equals ln of x, then 4 must be x. Or if you want, you apply e to both sides, and then it cancels the ln. So that's how you can get that. Okay. All right, so that's how you get this 4, and then this point right here, the x value is ln of 2 squared, which happens to be 0.48. So I calculated so that we can have it as perspective. That's somewhere in here. Okay. Okay. So if we need that point, that is ln of 2 squared, which is about 0.48. Okay, so this is the region. Okay, this is the region, and we are rotating about the y-axis. So this is x, this is y. So we are rotating like this. We are rotating about the y-axis, and this is the region. Now, again, notice that I haven't picked what equations I want to use for the blue and the red, even though I put this here because I'm doing these calculations. But I haven't decided yet what equations I'm going to use until I place my rectangle. Let's see. Actually, we only have one way of placing the rectangle, right? Perpendicular to the axis of rotation right now. But even if you had a choice, which pretty soon you will, you could put it horizontal, parallel to the axis of rotation if you want. That's not a wise choice, right? If you place the rectangle like this, parallel to the axis of rotation, from 0 all the way up to this ln of 2 squared, you will have only, the blue function giving you information about the rectangle. But then the moment that you pass that, the blue function is no longer needed. Then you have a little piece that is given by the line y equals ln of 2 from here to 1. And then after 1, you have the red function from below giving you information about the rectangle. Like 3 intervals you will need to calculate. That's too much, okay? So even if you had a choice, it's not really a good idea to place the rectangle parallel to the axis of rotation in this case. So if you put it perpendicular to the axis of rotation, it's always the case that the red is to the left, is to the right, and then to the left, right? We will integrate from 0 to ln of 2, and then everything will be fine, okay? Only one integral is needed. In other words, this is the smart choice to do. In our case, it's the only choice because we haven't talked about anything else. But the next section is another method that actually is a different formula because instead of placing the rectangle perpendicular, you place it horizontal to the axis of rotation. Okay? And then later on, you get to decide which one you use. Do you use perpendicular or horizontal? And you need to go through this thought process that I'm telling you. What's better for you? When I say better, is how can you compute the problem with one interval if possible? Okay. And here, and you need always information about the rectangle. Here, the rectangle is always given by the red to the right and the blue to the left. Okay, uniformly when you go from bottom to top. So that's the best scenario. If you put it parallel to the axis of rotation, too many things are changing as you move from left to right, and that's not good. Okay, so again, as you can see, because I have that, I don't even need to worry about when these functions intersect and so on. So that's why I was saying that the discussion above was not relevant. But if we didn't have the y equals 0, it will be relevant because you have this little piece down here that you will need to include in your region. And then you need that point, because to do this, to integrate with respect to y, you need to know how low you go. So you will need to know that little point. And you have to go through that business. Okay? That's the reality of it. But we are nice, and that's why we put y equals 0. But remember, my job is to tell you the whole story. Because when you are out there, nature is not nice. It's nice in its own way, but it doesn't mean that it wants to be nice to you and your calculations. Always keep that in mind. So, anyways, and you will have computers. So if you have to do a situation like that, a computer will do it for you. Your job will be to set up the interval. Then you feed it to the computer, right? Okay. So the region is clear. Now, why do we need to use washer and not this? Notice how there is a slight separation here between the region. There is this little piece here. There is a separation between the region and the axis of rotation. So when you rotate this, there is a shallow part. There is a hollow part that also is going to happen. Do you understand this? Yes.
Is washer always f squared minus g squared, or is it f minus g squared?
No,
A square.
You have to worry about R out.
Remember, is the radius squared, the outside radius squared minus the inside radius squared.
Okay, so then disk is the one that's
radius squared. There is no hole.
Yeah, so it's just radius.
It's just one thing. Okay. All right. So now that we have the rectangle, then we need to illustrate here the quantities that we mentioned above. So remember, we already know. So with this picture, you can already say, okay, what method I'm going to use. So what's the method? Washers. What's the variable? The variable is going to be y, right? So we immediately, with this information, we immediately can write that the volume is going to be the integral from where to where? From 0 to ln of 2. And then the formula is pi r out square of y minus r in square of y dy. So naturally, your question should be, okay, what's R out and what's R in? So let's go to the picture. What is R in the picture? What's R in the picture? In the picture, R in will be
Parabola minus.
no. In the picture, this little separation here. That's R in. The picture will tell you what's the formula, but let's first put it in the picture. Okay, that's R in. You understand this? And what is R out? Would be all of this. Remember, R out is from the farthest point of the rectangle all the way to the axis of rotation. Do you understand this? That's R out. And R in is the separation. The separation of the closest point of the rectangle, the distance between the closest point of the rectangle and the axis of rotation.
And it's R out minus R in.
Outside minus inside. Again, think about it. You have a washer in your hands. How do you find the volume of a washer? The outside volume, the big washer, and then remove the hole, which is the R in, right? Okay, so now that we have that in the picture, then the picture will tell us what formula to use. Let's see, according to the picture, how can we calculate R out? I'm delaying this because this is the thought process that you need to have. And the way I'm doing it is in general. No matter what region you have, no matter what situation you have, if you go through this thought process, you will get your formulas. Okay? Because if you look at the book, you see that the book gives you like 4 different formulas depending on the situation, okay? And what's the point in memorizing a bunch of formulas? Just understand what's happening and then adapt to the situation. So let's see.
R out, you would just use 1/2 L max.
Very good. Well, okay. No, before that, you use the red function, but we need to fix something else in the picture. What do I need to put in the picture? What formula should I use for my curves? What I have, or should I use the original one that was given to us?
The original one.
We need to use the original one because we're integrating with respect of y, so we better have x equals something, right? So here, I'm gonna return to my x equals 2 to the y, yes? And for the blue, I'm going to put x equals y squared. And those were the formulas given to us. Okay, so now with this information, notice that R out is entirely given. Remember, it's always right minus left, but here the left is 0, right? It's the axis. So it's just given by the red function. The blue function has no saying in the outside radius here. You understand this? So R out is just e to the y, e to the 2y. It's given by the red function. Let me put it in red. Is that clear? Okay. And then R in, how do we calculate R in? It's given by the blue function entirely, right? Let's look at the picture. The red function has no saying what the inside radius is, right? It's given by the blue curve entirely, so that would be y squared, right? Okay, that's x equals y squared. You okay with this? All right. So that would be the integral from 0 to ln of 2 of pi times. Now R out is e to the 2y. We need to square that. And then R in is y squared. We need to square that, dy. Questions? Okay, and now we calculate. So I will take out the pi. Now this is the routine part, right? So e to the 4y and y to the 4. And then locally, this is stuff that we can calculate, right? So we know how to integrate e to the 4 and we know how to integrate y to the 4. So what's the integral of e to the 4y? E to the 4y over 4, very good. And what's the integral of y to the 4? So 1 over 5, y to the 5th, and then we plug in from 0 to ln of 2. And remember, pi is multiplying all of this. So that would be e, so let's see, 1 over 4. So that's 1 over 4 times e to the 4 times ln of 2 minus 1 over 5 times ln of 2 to the 5th, and then minus, now I'm going to plug in 0. So be careful, when you plug in 0, you don't get 0 here, because now this guy becomes 1, right? e to the 0 is 1. So you're going to get 1 over 4 minus 0. And we calculate this. So we are not going to be able to get an exact answer. I mean, we'll get an exact answer, but it's not going to be pretty, but that's okay. So let's just simplify this. So here's what I'm going to do, okay? Just I don't want to write all those steps, so I'm going to say them out loud. So this 4, I'm going to bring it here. They're going to have a 2 to the 4, which is 16. Then the e and the ln cancel out, and you get 16, right? That 16 divided by 4, what gives you? 4. So that is a 4. Is that okay? Okay. Then minus, then this one is what it is ln of 2 to the 5th power over 5. I cannot do anything about that. Minus 1 over 4. And so we can at least combine the 4 and the 1 over 4. So that's 16 over 4 minus 1, that's 15 over 4. So we get 15 over 4 minus ln of 2 to the 5th power over 5, all of this times pi. That's the exact answer, and You know, if you want approximation, then actually let me plug it into my calculator because I better get a positive number. If we get a negative number, we know something is wrong. This is volume, right? But you know, the good thing is that ln of 2 is negative to the fifth is negative, but then with the minus is positive, so I know this answer is positive. Okay, I know this answer will be positive. But let's calculate it anyways. So ln of 2 to the fifth power divided by 5, make it negative, then plus 15 divided by 4.
Can you explain how you got that? I'm trying to do it in a breakout.
Hold on, nice part. My calculator, I have to follow the order of operations otherwise, because I cannot put the expression, and I need to focus. So this is about 11.68 you should get. Okay, so what's your question?
Can you tell me how you got that for? I'm trying to solve it in my head.
Okay, I told you out loud. So this 4 comes here as a power. What's 2 to the 4?
16.
16. So E and ln,
That's
it cancel out, so you get 16 over 4, which is 4. Right? Okay. Again, this last part is important. It's multiple choice, right? You have to get the answer right. But really the important thing is to be able to set up the integral correctly, okay? Do you have questions on this problem? No? Okay, good. So let's go ahead and let's do another one. Let's see, how about this one? Now here we can go faster. And the region is gonna be easier to analyze. So here we have a line. We have a parabola, and let's rotate about y equals -1, okay? So the previous example, the axis of rotation was a vertical axis. This time the axis of rotation is the horizontal axis, okay? All right, so what's step number 1? Sketch it. All right, so this is gonna be a line and a parabola, right? So they could meet, so let's go ahead and let's figure out the points that they're gonna meet before we do anything. So x plus 2 equals x squared, and let's solve this equation. So that would be x squared minus x minus 2, and we can factor that as x minus 2, x plus 1. So we have x equal to x equals -1. Yes, so we know we're gonna have 2 points of intersection. Let's do it. So we have the line y equal x plus 2. So what's the y-intercept of this line? It's 2. So 1, 2. And what's the x-intercept of the line? -2. So it's gonna go to 2, 0,2, 0,2 and 2 and -2,0. Okay, so we have this line here. So that's f. Okay, and now we have the parabola y equal x squared, and we know that they're gonna cross when x is 2 and -1. So here is -1, and they cross right here. I'm just sketching square function, right? And then this other point of intersection, we also know it. This point here, we know what it is. This happens when x is equal to 2, and the y value here is 4. Okay, so, and that's the function g. And we were not told anything else, so that means the region is the one that's bounded between these two functions. So it's clear that it will be this. Does everybody understand that this is the region that we are rotating? Yes?
Yeah.
Okay, next we need to see what is the axis of rotation. What's the axis of rotation? Y equals -1. So what's the graph of y equal -1? Okay. Can I tell you a joke? Every line is straight. Right? So people tell me, straight line. Okay. What do you mean? but I know what you mean. That's why. Okay, so -1 right here.
You're saying every line is a straight line?
Yes,
What if it's,
as a curve.
okay, I mean, but a line can curve.
And it's
Right.
not.
Then it's not a line anymore.
Forever.
When we say straight line, it's kind of right.
Redundant, yeah.
It's like, okay, maybe not everybody here speaks Spanish, right?
Poquito?
Okay. No, I was gonna say something like when if you say
Anyway.
voy a subir para arriba, yeah, you know, I basically yeah, but you say you can say go up, go down. So in English, I don't know, it doesn't happen in English,
Okay, yeah, fair enough.
right? Basically, just saying twice that you're going up. In that expression that I said, you're saying twice that you're going up. So, okay, so anyways, let's go here. I want to use another color. Green. No. So our axis of rotation is this line. Y equals 1. We are rotating about this line. You okay with this? All right. So again, we don't know much. All we know is that we can place rectangles perpendicular to the axis of rotation. That's what we're gonna do. But even if we had a choice, do you think it would be better to place it horizontal? In this case, will it be better to place it horizontal? It wouldn't be better, right? Notice that here, if you place it vertical, it's always the case as you move from left to right that the red is on top and the blue is in the bottom, right? If you place it horizontal, what's going to happen? As you go from 0 to 4, you will have to be doing with respect of y. But the thing is that from 0 to 1, this piece right here is only blue on both sides. And then it's blue to the right, but then red to the left, right? So you will need two integrals and deal with that. So it's easier anyways. If you had a choice, which you will after next section, in this situation, it's easier to place it like this, perpendicular to the rotation. But remember, this tells you the method. Because we have three methods. This, washers, which is what we're doing, and shells. Which one do you use? This guy tells you, the rectangle. Okay, how you place it, that's how you know the method. Okay, are we okay with the picture? All right, so what's the method? Washers. Why not this?
Because there's a gap
Very good.
in the axis of rotation and the function.
So I'm gonna use washers, and there is a super gap here. Right? Even if it was the x-axis, there was still a gap because we have all of this piece, all of this part right here, right, and this little piece over here. That will be smaller. But anyways, I moved the axis a little bit more. It didn't make it the x-axis. I make it y equals -1. Now we have all of that gap that I mentioned above plus this rectangular strip, right? So, okay, so washers. What's the variable?
X.
So the variable is x. Does everybody understand that the variable is x? Remember, the position of the rectangle perpendicular to whatever axis perpendicular to, that's your variable. Okay? Because here, to sweep the entire, to cover the entire region, how do you move the rectangle? From left to right. Because perpendicular, you have to move it like this, from left to right. Yes? If you put it horizontal, you move it from bottom to top. That would be y. Okay? All right. So with this information, we immediately can write the formula. From where to where is the volume? From -1 to 2. Good. And then that would be pi times, and then open parentheses, r out squared of x minus r in squared of x. So in other words, we need to figure out a formula for r out in terms of x and a formula for r in terms of x. So we should go to a picture and see what these things are. So remember, r in is this fellow over here, is the gap, and then r out is all of this. From the top of the rectangle all the way up to the axis of rotation. Yes? Look at the picture. What's r in? How can you figure out r in, which is this gap right here?
You would do the g function minus r line, which is sort of the g of x minus -1.
Okay, good. So yes, that's how you do it again. But the same thing as saying +1, right? So it's just that I want you to think You don't go out. Okay, yes, you always do top minus bottom, but just it's the same thing what I'm about to say. But notice that you always have a fixed distance here of 1, right? So Rin would be 1 plus whatever this little piece is.
Okay.
Right?
Right.
So 1 plus G. It's the same thing that you said, because
Right.
G minus minus 1 is G plus 1, right? But the point is that Rin is going to be 1 plus this little piece, and using the same idea, R out is going to be 1 plus this piece over here, which is given by the red.
Oh my
So
God.
1 plus G,
Because
1 plus
it's
F.
not 0.
It's not 0.
Because
It's
it's
just you need to go
So
down
if
all the way
it
up
was
to.
0,
Oh,
you wouldn't do that.
Why didn't you complain here? It should be y equals the equation. -1. Yeah, if it was the x-axis, then R in would just be G, and
You
R out would just be
explained
F.
why I keep getting the same questions wrong. You just explained it to me.
He said that a few times.
So you can either do it, top minus bottom, but it's kind of nice to see that that R in you can do it by doing 1 plus and then the function G.
Oh my God, that's insane. Okay, wow.
Do you understand this?
Yes.
And what is R out? Very good. So 1 plus whatever F is. Because if we have the gap, which is 1, and then the rest to calculate R out would be from the x-axis all the way up to the red
So
function.
it's the 1 plus and then all of that squared.
Yeah, and we'll put it.
Like the 1 is also squared.
Yeah, the whole thing. That's
Oh my God.
that's what that is. That's
Oh my
very
God,
simple
okay.
too. Okay, so let's see. So R out is gonna be 1 plus what is F? What was F? X plus 2. So that's x plus 3, right? And then R in is 1 plus x squared. And that's it. That's as far as we go. So let's write it down. So this is going to be x plus 3 squared minus 1 plus x squared squared dx. Questions?
So then if, like, let's say, for example, our axis of rotation was y equals 1, then we would subtract 1, right? Because we're not doing.
That would be more complicated because we'll be in the case in which there is piece of the region that's being overwritten. You see, if you say y equals 1, then you see the axis is actually cutting, so the region is not on one side. So far, we're only dealing with situations in which the region is on one side of the axis.
Okay.
If it's y equals 1, you have a piece of the region above the axis and another one below.
Right.
So situation that is a little bit more complicated because there is.
One
You
half.
will be over calculating the volume. If you just use the formula blindly, you will be calculating more than what you have to. Because there are pieces that are overriding themselves.
Wouldn't you use the axis of rotation and then you would do the function minus that, and then on the other half if it was the same function, you'd do that function minus that and do 2 intervals?
It's just that the solid that you obtain is weird. It would be twisted. If you have something like this, and I put the rotation. If you rotate this, you get a strange solid, I think. It's not going to be something nice. It will have gaps, but then what happens with this part that is on the axis, like it's being twisted somehow.
That would make it hourglass, basically. Right? You would have, because of the angle, you'd have 2 different.
Maybe if you have something like
2
this.
different tones.
Yeah, but you have to have something like this, right? Then that little point, and if you do the axis of rotation here, let's say if you have something like this.
If we would have x equals 0.
Okay. But okay, the point is that if the axis of rotation is actually going through the region, it's more complicated. These formulas do not work. The formulas, how do we get these formulas? We got them in the situation in which we are away from the axis of rotation. At best, we are touching the axis, but the axis is never going through the region. If it goes through the region, you have to do a completely different analysis. Because the solid is, there will be something twisted. You see, side rotating something like this, you'll be twisting this part right here. We're going to be twisting this. I don't know if you understand what I mean when I say twisting stuff. So no, if that's the region, you're not going to get y equals 1 as your axis of rotation. Okay? That would be a completely different situation that we are not actually analyzing here. Okay.
If we have y equals 0, we would just use this method, right?
No. When you say y equals 0, that's the x-axis.
Yeah, I mean using just the x-axis without the condition of y equals -1.
And yeah, if it's y equals 0, that means that the line is actually the x-axis, but you still have to use Washers because you see there's all this gap here. The region was yellow, right? If your line is the x-axis, you still have this gap that you have to, that will generate a hollow part in your solid. It's only when the entire region is touching the axis all the time that you use this, okay? Only when it's touching the axis all the time. Like, I don't know, something like this, and then the axis of rotation is this line, and let's say this is the region. That's this method, because the region is touching the axis all the time. There is no gap between the axis and the region. But if it separates from the axis at least a tiny bit in your interval, that's it. You have a hole, so you have to use Washers or cylindrical shells. And when we get to talk about it. Okay. Anyways, but are you okay with this? All right. So now comes the tedious part, which is to compute this. So let's get it out of the way. So that will be from -1 to 2. Okay, so this one, we can do it by power rule, because notice that x plus 3 works the same way as if it's just x. Think about it, making a little substitution. If you let u be x plus 3, then du is just dx, so it's the same thing. So it's like integrating u squared. So what I'm saying is the integral of x plus 3 squared is x plus 3 cubed over 3. Okay? So I'm gonna do that instead of having to span the big parentheses. But I will do that later. First, for the other one, for the blue, I have to span the parentheses because I cannot play the trick anymore because I have an x squared here, right? I will need an x down outside here to be able to play that trick, and I can't. So I'm not gonna touch that. I'm doing it just to simplify my calculations later, because then I'm gonna have a big expression. We're already getting a big expression here. Even though, okay. Let me just keep it simple. So I'm gonna span, just to keep it simple. And this is 1 plus 2x squared plus x to the 4. Okay, now if you don't mind, I'm going to distribute the negative and combine like terms already, if we can, okay? So I will have this x squared with this -2x squared becomes -x squared, right? So that would be -x squared. Then the 6x stays there. Then 9 minus 1, that's 8. And then minus x to the 4 dx. So we get pi times, and this would be minus x cubed over 3 plus, okay, that's 6x squared over, okay, let me just write it down. 6x squared over 2 plus 8x minus x to the 5 over 5 from -1 to 2. And now we have to plug in these numbers. Simplify. It is. So, but you know, that's what it is. Again, if I'm doing it, you cannot complain. You have to do it. Okay. So we plug in the 2. What do we get? So we have -8 over 3 plus 6 over 2 is 3 times 4. That's a 12 plus 16 minus 32 over 5. That's what we get when we plug in 2. And then when we plug in -1, in situations like this is why you saw me last time. I saw a symmetry and I jumped right into it and cut the -1 and put a 0. Because you see, if we had a 0, then this parenthesis would just be 0, so it would be something nicer. But unfortunately, there's no symmetry and it's from -1, so we have to plug it in. Now here you have to be careful with the signs. So put -1, the negative survives, but then cancel with the negative outside. So I get positive 1 over 3. Yes? Plug in negative 1 here. That's negative 1 on top, but there's a minus in that term. That makes it positive. That's why you see 1 over 3. Then plus 3. This is 3x squared. You put negative 1, that's just 3. Then minus 8. And again, plus 1 over 5. Because the negative 1 survives the x to the 5th, but then the minus makes it positive. Okay? And now we combine. Let's see. So I can combine this guy with this one. So negative 8 over 3 minus 1 over 3, that's negative 9 over 3, which is negative 3. So let's see. We're big guys, so we can do this. 12 plus 16, 28. Minus 3, 25. Plus 8, 33. And then I'm gonna do this one with this one. So negative 32 over 5 minus 1 over 5. That's negative 33 over 5.
Professor?
Yes.
Isn't 3 supposed to be negative in the second last parenthesis?
Second last part. This one?
Yeah.
Why? When you put negative, that's because of this guy. When you put negative 1 here, the square kills the minus.
Oh, okay.
Right? I mean, eventually it will be negative, but because when you distribute this.
Yes.
Yeah. And then, okay, that's 30, and then we just need to do 30 minus 33 over 5. It was not that bad. So 30 minus 33 over 5. So times 5. So 150 minus 33. 117? Yes, 117. So 117 pi over 5. The answer is, but it's simplified nice, at least. Okay. Are we okay with this? Yes.
On a test, will we be marked wrong if we don't reduce an answer all the way? Like if that was reducible, like it was 120 over 5, right? Would we be marked wrong or partially wrong if we left it like that?
If it's a multiple choice, you'll see.
You see, so you guys love multiple choice. The problem with multiple choice is that if you don't get this, right, you have to get it right all the way to the end. If it shows your work, if you don't get this number, it's just minus 1 point, right? Say the question is 10 points. You already have, I don't know, 5, 6 points for setting up the interval. The rest of the 4 points is okay. Can you now calculate it? Because really, my purpose here is that you can get to this point, right? If you can do this, if you can write this part right here, I'm happy. Or the one above, right? The rest is calculus 1. That's what you did at the end of calculus 1, right? So if a question is worth 10 points, at least 6 points you will get it. It's more than half. 6 points or 7 points, I don't know. I have to see depending on the complexity of the problem. But let's say 6 points for this. Then the remaining 3 points you have to earn. Right? It showed me.
It's like Einstein. He gave the formula, but he didn't solve the problem.
Yeah, there is a famous conjecture. Well, it's not a conjecture anymore, but by Fermat. That he said, "Oh, this problem is pretty interesting. I know how to solve it, but I don't have space in the paper." And then 100 years later, was that someone was able to actually find a solution for it. That's Fermat's last theorem. That's the one that's called Fermat's last theorem. It was a conjecture and was proved by Underwood in 1995. And this is from the 1800s. In 1995, someone actually was able to prove it. And he just said, I don't have enough space. So I know this is true, but I don't have enough space to write the answer. Anyways, so, okay. So yeah, if it shows your work, you are an advantage. If it's not show your work, you have to, And unless, you know, the question is, the choices are, I just ask you to set it up and not to solve it. And then you just have different intervals there and you need to pick which one is the one that works for you. Right? That could be a style of question also. Okay. Questions? Now, for example, in the homework, you have to compute it. And if you don't get the number, like one of you asked me a question on the forum about the area, but you were off by 100 points, by 100, your numerator was off by 100 or something like that. And then I replied, show me what you did. Let me see your integral. Because I cannot tell you what you did wrong. If you got 3 instead of 5, well, what did you do? I don't know. So, okay. Questions on washers? No? Okay, so, okay, I'm gonna do the same thing that I did last time. I have 10 more minutes. And let me ask you a question pretty quick. Imagine that instead of y equals -1, the question would have been rotate about x equals 3. Same region. So, question? How about rotating the same region, exactly the same region as above, but about the line x equals 3. So I'm gonna go here, and let's say 3 is over here, and then this is the line x equals 3, and we want to rotate about this line. Okay. So our discussion.
Your inner radius would then be 3 minus the left.
Yeah, but first of all, if you want to use the knowledge that we have right now, you will need to change the way that we place a rectangle. Yes, because it has to be perpendicular to the axis of the rotation if you want to get washers. So your rectangle will have to be the other way around. You will need a rectangle like this, right? And then, but what's the problem with this? According to the discussion that we had mentioned before, that then you have to split and calculate 2 intervals. Because your variable is y now, so from 0 to 1, the rectangle is only given by the blue function in both right and left, right? And remember, the thing is that this is y equal x squared, but then you have that x is plus or minus square root of y, right? So the right part is positive square root of y, and the left part will be your equation for negative square root of y. You have to take that into consideration.
So you have to do it twice, one with the negative y and one with the positive, sorry,
No,
one with the
no,
negative square root of y and one with the positive.
No. No. So you need 2 intervals, one from 0 to 1 and another one from 1 to 4, right? Now, from 0 to 1, when you have to work with this rectangle, why 2 intervals? Because from 0 to 1 is only the blue. Now, your inside radius will be given by this part of the parabola, which will be square root of y. Your outside radius will be given by this other part of the parabola, which is negative square root of y. Okay? And then your second integral will be from 1 to 4, and your inside radius will be given by square root of y, this part of the parabola, and then your outside radius will be given by the red function. It's a line, so that's easy. You will solve for x. That will be y minus 2.
And for both of them, you subtract the 3. For both of them, for both integrals.
Okay. Yes. Okay. Good. Actually, when I said it's given by that, but yes, you actually have to do 1 plus. You see. The gap is always 1 here. Because when I say the blue, you are only taking, actually it's even more than that. It's actually more. It's actually 3 minus this quantity. You see the whole thing is 3, and then the whole is going to be 3 minus whatever the blue tells you. So it will be 3 minus square root of y for the inside hole. You understand this? And then the outside radius is going to be 3 minus y minus 2. The point is that if you put it like this, perpendicular to the axis of rotation, it's not a good idea. First, you will need 2 integrals, and second, you have to deal with all of the things that I'm telling you, okay? But the fact that we need to calculate 2 integrals is not good. If we can avoid it, we should. How can we avoid 2 integrals? By leaving the rectangle the way we had it. But then this requires a different method. Because when you rotate a rectangle, all of a sudden now it's parallel to axis of rotation. It's no longer perpendicular. What happens when you rotate a rectangle parallel to an axis of rotation? You get a different shape. You don't get this. You don't get a washer anymore. You're gonna get what we call a cylindrical shell. Think of a cylindrical shell as a toilet paper. Okay? Yeah, exactly. A ring with some sort of thickness. Yeah, that's what we're gonna do in 2.3. So this problem, I'm using that like as a leap towards that. Okay? Because if it would have been about this line, same region about this line, all of a sudden the technique that we're discussing is not good. We should use another one. Okay? Yes.
When we've been speaking about rotating things with respect to the y-axis, has been the furthest right function minus left. So if you're now using, say, x equals 3, would you then switch that and be taking the furthest left function minus the furthest right?
So remember, it's always when something is horizontal, it's always right minus left. Always. So if you want to know when you draw the picture,
It wouldn't matter
this would be your R in, right? This piece right here, for example, would be your R in. How do you calculate it? Right minus left. What's the right? 3. What's the left? The blue guy. Right?
How do you find that distance?
I just told you. Right minus left. So 3 minus whatever this function is.
Yeah.
Right? Which in this case would be square root y.
That's not what I thought you were saying.
Okay? And then the outside will be the distance from the blue line all the way up to the red function. So it will be 3 minus the red function, which in that case will be y minus 2 when you solve for x. Remember, when something is horizontal, you find it by doing, you will always find horizontal stuff by doing right minus left. When something is vertical, you find it by doing top minus bottom. Right? So, okay, so the observation that I wanted to make is that if the question was like this, it's not really convenient to use what we are doing, so a new idea is needed. And this is just to make a transition to shells, okay? So how about rotating this? So if we use washers, because there is a hole, because there is a separation, so cannot be this. So if we use washers, we will need, we can do it, but we will need 2 integrals. Everybody understand why we need 2 integrals? So this is not good. So this method is not ideal for this situation. It was ideal before, but it's not ideal now. I don't want to say it doesn't work. It works, but it's not ideal for this situation. So in this case, we can use another idea or another method, and that method is called cylindrical shells. Okay, and let's see, 4 minutes. Can I do it in 4 minutes?
No.
It's just that I want you to be able to work on the homework. Otherwise, you have to wait until Tuesday until you can start working on 2.3. And I want you to be able to start working early on. I will move the due date, but what if you want to do it on Saturday? So let me just tell you quickly the story, and that way when I come on Tuesday, we can jump right into examples. I don't have to repeat the whole story. It's taking half the class to make it. Okay? So again, the point here is that we want to deal with the situation in which a rectangle is parallel to the axis of rotation. Okay? So parallel to the axis of rotation. So rectangle, put it here. This is when the rectangle is parallel to the axis of rotation. Remember, this is how you can identify the method. Before the 2 methods that we have discussed so far, the rectangle is always perpendicular. This one, the feature is that it's parallel. So picture is, you have your rectangle. You have your rectangle here, and then this time the axis of rotation is here, or maybe you have your rectangle like this, but then this time the axis of rotation is like this. Okay, so when this happens, what sort of shape is created? So we have a rectangle, is gonna have a copy over here. Okay, and the point is that when you rotate, this is gonna happen. Yes? So when you pull out the secret weapon, this is what you get. Literally, this is what you get. Okay? And then what's important here for us is this distance right here. I'm gonna call it R, which in the picture is the radius of the inner circle, right? And then I'm gonna care about this. I'm gonna call it H. That's the height of my rectangle. In the other situation would be, I guess, the length, but I'm gonna still call it H. And then let's see, what should I use here? Delta what? Delta Y or delta X? For the thickness.
Well, it's like this. Oh, wait, no.
Delta X. Very good. Remember, the variable of integration, delta X is your variable X. I mean, here you will use your variable of integration. Which one is it? Well, my rectangle is perpendicular to the x-axis, right? So my variable is X. You understand this? All right, so this delta X represents the amount of toilet paper that you have, right? That's the thickness of your cylindrical shell. Do you understand this? Now, and then you can imagine what's the other picture, right? So the other picture is similar, but the other way around. Again, this is R. So R is the distance between the rectangle and the axis of rotation. Now here, H is actually the length instead of the height of the rectangle. And what is the width? Delta Y. Okay? Now, how do we calculate the volume of something like this? So remember, the idea here is that we're going to approximate a solid, right? So if you want to approximate the solid, then the shells that we're going to have are going to be actually pretty thin. They're not going to have this many toilet paper. They're basically going to have no toilet paper, because the idea is that delta X or delta Y, whatever it is, it goes to 0, right? In other words, we're going to be dealing with this fellow. No paper at all. In the limit, you have no paper. And what do? Use water. But you have to do something, right? The point is that as I'm going to do it here for X, but it's the same thing for Y. So as delta X approaches 0, then our cylindrical shell is going to look like this. It's going to get approximated by this. Do you understand this? So it will be approximated by this shape. This is as delta X approaches 0. And that's why we only care about R, because now R is the one that is down here. Let me use this color. How do we calculate then? And the idea is the same. We're going to integrate the volume of this to get the volume of our solid. Okay? So how do we calculate the volume of something like this? Here is the other trick. Anybody has a scissor? No? Should have brought a scissor. So if I cut this, what shape do we get? Get a rectangle, right? So if we cut this, so cut, then we're gonna get a rectangle. Now, I get a rectangle. What would be the top side, red or black? It would be red, right? It's the circle that open up, right? So you cut it, you get this, and so remember that the volume, there is a little thickness attached to it, right? Which is the infinitesimal thing. So it's area of this times the width, right? The width we know is the dx or the dy. Now, how we calculate the area? We need to know the red. The black is easy. What's the black? The black was h, right? What's the red? The circumference of the circle. Very good. Which is 2 pi r. So what's the volume? So the volume can be approximated by 2 pi times r times h times the thickness, which would be either delta x or delta y, depending on your variable. So how do you calculate? So in the vertical case, the formula is, this this is not a good time to lose battery. So the formula is from A to B, 2 pi r of x times h of x dx. And then in the other case, in which it is horizontal, the formula is the integral from c to d 2 pi, but now the variable is y, r of y, h of y, dy. And remember what is r? R is the distance between your rectangle and the axis of rotation, and h is your height or length of the rectangle. Okay? So
H gets given to us usually?
it's the rectangle.
Oh.
You have to figure it out with the region, right? All of this begins with placing your rectangle. You put your rectangle, and then the rectangle tells you everything else. Okay? Anyways, on Tuesday now, we have the formulas. We can come in and just do examples. Okay?